Today, I would like to tell you about one of the facilities of the Joint Institute for Nuclear Research. It is the superconducting heavy ion synchrotron, known as the Nuclotron. But first, what is a synchrotron? The idea of such an accelerator was put forward in 1943 by the English scientist Marcus Oliphant. He described it in the following way. Particles should be constrained to move in a circle of constant radius, thus enabling the use of an annular ring of magnetic field, which would be varied in such a way that the radius of curvature remains constant as the particles gain energy through successive accelerations by an alternating electric field applied between coaxial hollow electrodes. Oliphant did not develop this idea and didn't write any math supporting this method of acceleration due to a lack of energy or time. The theoretical framework of this method was established by a member of the Academy of Sciences of the USSR, Vladimir Wechsler, who in 1944 formulated the phase stability principle. In a few words, this principle is postulated as follows. At certain conditions, the particles from an initially continuous beam are sequentially bunched, which follow the frequency of the accelerating field and steadily gains energy. This principle was tested for the first time in Great Britain at the Royal Arsenal Laboratory in Woolwich, a research centre involved in the British nuclear weapons programme. There, the existing 4 MeV betatron was converted to an 8 MeV synchrotron, demonstrating the potential of the principle. It has been more than 70 years since then. Synchrotrons have gone through a substantial period of development. The main parameter that characterizes synchrotrons is magnetic rigidity. When the first synchrotrons, working only on one particle type, were created, this parameter was usually forgotten, and only the maximum energy level was mentioned. But if we talk about a synchrotron accelerating various particle types, the energy at the accelerator exit will depend on the particle charge and mass number. What is magnetic rigidity? It is the effect of particular magnetic fields on the motion of the charged particles. The product of the bending radius multiplied by the magnetic field is the magnetic rigidity. Magnetic rigidity is measured in Tesla meters. For example, the magnetic rigidity of the nucleotron, which I have been telling you about, amounts to around 42 Teslas multiplied by 1 meter. How much is it in terms of the energy of accelerated particles? One of my colleagues, a big fan of programming and a doctor of science in physics and mathematics, created a small programmable calculator capable of recalculating various particle parameters, including magnetic rigidity and kinetic energy. Here is a picture of this calculator. It collects all the formulas needed to do the calculations. I use this calculator because I'm too lazy to do the math on a piece of paper. By using this calculator, we get the following result. 42 Tesla meters amounts to about 11.7 gigaelectron-volts of kinetic energy for protons and 4.2 gigaelectron-volts per nucleon for gold ions with a charge number equal to plus 79. That is to say, for the gold nuclei. Initially, synchrotrons, like other accelerators, were constructed based on the concept of room temperature magnets. At some point, it was proposed to use superconducting magnets to form the trajectory of the charged particles. What inspired this idea? First and foremost, it would make it possible to increase the energy in the existing accelerator tunnel. The first superconducting accelerator was named Tevatron. The project of this accelerator came about due to the desire to double the particle energy and increase it up to 1 teraelectron-volts in the existing tunnel. The existing tunnel was equipped with warm magnets, which were able to accelerate protons up to 500 gigaelectron-volts. The initial project, called Energy Doubler, was based on the usage of superconducting magnets. From that moment on, the technologies for the mass production of superconducting cable and the mass production of magnets were developed. The magnetic field in the Tevatron magnets was 4.5 Teslas. The magnet of the Large Hadron Collider is at the moment 8.3 Teslas. The Large Hadron Collider project had the same task to obtain the maximum particle energy in the existing tunnel. For future accelerators, the possibility is being considered to create magnets with a magnetic field of up to 20 Teslas. Here, the challenge of reducing their size is being considered because the perimeter of such an accelerator would need to be around 100 kilometers. The creation of the Nuclotron accelerator had completely different objectives. The primary challenge was to considerably reduce the size of the accelerator. Superconductivity, in that sense, is advantageous, because in the copper superconductor the density of the current is about 3 orders of magnitude higher than that of regular copper. This makes the coil and the magnetic yoke compact. Therefore, there was no need to obtain the maximum field value. If there is no need to achieve the maximum field value, an iron yoke can be used to form the field. The iron gets saturated at around 2 Teslas in the magnetic field, while the quality of the field deteriorates. An iron magnet with a superconducting coil can be created up to 2 Teslas. What are the advantages of such a combination? First, as I have mentioned before, it's a win in terms of the size. Second, it's a win in terms of energy supply. A superconducting coil doesn't have any energy loss during the heating of the coil, because it is not cooled down with water but with helium. However, there are energy losses during the process of recooling the liquid helium after it has cooled down in magnets. A significant amount of power can be saved through the proper magnet design. Among other things, the Nuclotron magnets, meaning the superconducting magnets with iron yokes, turned out to be more effective in terms of their operational safety, are technologically simpler, and much more efficient than non-superconducting magnets. This technology was developed and implemented at the Joint Institute for Nuclear Research. The Nuclotron consists of exactly such superconducting magnets. The magnetic systems, except for the bending magnets, which I have talked about before and which have a greater field size, consist of a number of various magnetic system elements. The magnetic system elements of an accelerator can be divided into 2 groups, structural and built-in. Structural magnets are dipole magnets, which form the geometry of the orbit, and quadrupole magnets, which provide beam focusing in the transverse direction, or in technical terms, they provide the required frequency of transverse oscillations of particles in the accelerator chamber. Furthermore, to compensate for the error and nonlinearity of the main magnetic field, several types of correctors are used. These are low-force dipole magnets in addition to quadrupole, sextupole, and octupole magnets, and its various modifications. As inserted devices in a synchrotron, elements of beam injection are used. These are septamagnets and kicker magnets, the so-called kickers. There are also beam extraction devices. For slow extraction, additional quadrupole lenses are needed to displace the particle oscillation frequency into the region of nonlinear resonance. For the resonance excitation, sextupole lenses are required. In some cases, one needs to make the so-called bump of the orbit control displacement of the beam orbit. To that end, bump magnets are used. We already know everything about the synchrotron, so why are we suddenly talking about synchrotrons again, and more specifically about the nucleotron? Once British scientists concluded an expert survey in order to find out what was the most complicated device ever created by humans throughout history. The experts were to choose from a whole set of various devices, starting from a space satellite and ending with a Formula 1 racing car. The accelerator complex won the survey. Why did it win? Because, by the number of systems or subsystems and by the complexity of their interactions, it surpasses anything else created by humans. Among other things, the inner processes of an accelerator requires complex mathematical and theoretical calculations. The accelerator itself requires very complicated fine-tuning. Many algorithms have been developed especially for accelerator tuning. The standard courses on accelerators deal in detail with each of the individual systems, their subsystems, and their operational principles. The purpose of my lecture today is to introduce and The purpose of my lecture today is to introduce the accelerator in general, describe what it looks like, and then deal with its separate subsystems. I'm not the first to do so. On the screen, you can see the cover of a book issued in 2014. Its editors were Valery Lebedev and Vladimir Shiltsev, who had been working on improving the parameters of the world's first superconducting accelerator, the Tevatron, for about 20 years. The book was actually called Accelerator Physics at the Tevatron Collider. It consistently describes in detail all the systems and subsystems of the accelerator, the story of its creation, and contains theoretical material, which is perhaps one level deeper than in most textbooks. As for me, I am not going to try to take on such a global challenge, but I am going a similar way. Therefore, I would like to tell you more about the Nuclotron.